Chapter 5, Number 23. A force of magnitude 7.50 Newton pushes 3 boxes with mass M1 equals 1.3 kilogram, M2 equals 3.2 kilogram, and M3 equals 4.9 kilograms, as shown in the figure. Find the magnitude of the contact force between box 1 and box 2, and then the one between box 2 and box 3. So this is sort of a classic standard problem, and we're going to just grind it out the normal way. So we're going to say we have some free body diagrams. For convenience, we're going to ignore vertical forces because we know that in these contexts the vertical forces will just cancel. So they're not that important. And, oops, maybe I don't really like where I drew that guy. So, give myself a little bit more room here. So let's look at our free body diagrams, and what we start with is a horizontal force F pushing on 3. And even though the problem reads that it pushes 3 boxes, in fact that force only pushes 1 box. It pushes box number 3. And then the 3 can't go through 2, so 2 is pushing back, and I'm going to call that force F sub B for no particular reason. You'll see in a minute why I called it FB, but it's the contact force from 2 on 3. It's a normal force, which prevents 3 from going through 2. It prevents interpenetration. The other way to prevent interpenetration is not just to slow down 3, but to move 2. And the way that happens is that by Newton's third law, 3 exerts a force on 2, which is equal in size, but opposite in direction. Of course, 2 can't go through 1, so 1 must be resisting. I'm going to call that FA, which is why the other was FB. And then, because 2 is pushing on 1, it will feel a force, which by third law will be the same size, but opposite in direction. And then all of these boxes, all of these things have an acceleration, which will be to the left, and it'll be the same for all of them because they can't go through each other and they can't flex. So we'll have something like that. From the free body diagrams, all right, so we'll have that the sum of forces on 1, and we look here and we say, oh, it's just minus FA. And I'm putting the minus in because we traditionally do our axes as, y and x. There's no good reason for them to have made it going left. There's no reason I couldn't make my axes left, but just to be consistent with what we've done, I'll put this in way and we'll say there's a minus sign. You'll see in the end these minus signs will show up and then they'll all go away. Likewise, from the diagram, the sum of the forces on 2, well, there's an FA pointing to the right, and there's an FB pointing to the left, and I'll indicate the leftness with the minus sign there. And then on box 3, there's an FB pointing to the right, and there's F, but it points to the left, so I'll put a minus sign there. These are, as I said before, they're all coming from the diagram, free body diagrams. And then we also have, of course, that the sum of the forces on box 1 has to be box 1 times its acceleration, which is m1 times minus a. And the force on box 2 has to be its mass times its acceleration, which is m2 times minus a. And then the force on 3, the net force on 3, has to be the mass of 3 times its acceleration, which is m3 times minus a. This is where you can see that all these minus signs are sort of going to be floating around, but then I can just cancel them out. And this, remember, is coming from Newton's second law. But sigma F1 is just sigma F1, so I can combine those and I can say that I have that m1 times minus a is equal to minus fa, and m2 times minus a is equal to fa minus fb, and m3 times minus a is fb minus f. I'm going to go to another page, and when I do it, I'm going to pull a magic trick, and I'm going to multiply everybody by -1. And so these minus signs will go away, and these guys will flip, and these will flip. So we end up with M1A equals FA. And M2A is FB minus FA. And M3A is F minus FB. And I wrote those in a particular way because what I'm going to do now is I'm going to say, well, what if we just were to add that equation and that equation? So we add that and we add that. And we say, what comes out? Well, on this side, we end up with M1A plus M2A plus M3A, which we can basically also pull out and say M1 plus M2 plus M3 times A. On the right-hand side, we get some kind of weirdnesses going on. We have that FA minus FA, right? FA plus minus FA, that's really just 0. And FB plus minus FB is really just 0. And so when all is said and done, all we have over here is F, which allows us to say that the acceleration is the force over M1 plus M2 plus M3, which is kind of neat. It says that the force applied, 7.5 newtons, over the total mass, which is 9.4 kilograms, and that gives us 0.7979 meters per second square, where I'm keeping an extra sig fig because we don't care about A, but we're going to use in a lot of calculations. What we really care about is FA and FB, and we can get them by going back to these equations and using any one of them, really, but for each thing that we want. So we'll go here and we'll say, let's take the first equation, which is in red, and we'll say, well, FA, the thing I want, is M1A. So it's 1.3 kilograms times 0.7979 meters per second square, or 1.03727 newtons, which becomes really 1.04 newtons when we go back to our 3 sig figs. And then we're going to do something similar, and we're going to say that, so let's go here, and we're going to take the blue equation, and we're going to say that FB minus FA is M2A. So FB is FA plus M2 times little a. So it's going to be the 1.04 newtons plus 3.2 kilograms times 0.7979 meters per second square. And we're going to get 1.4 3.59328 newtons, which of course becomes 3.59 newtons. And then we even have sort of a last option, which is we can check this third equation, and it should also be true if we have the right answers. So I'm just going to take the left-hand side and the right-hand side and see what happens. So the left-hand side of that equation is just M3A, which is 4.9 kilograms times the 0.7979 meters per second square, which is 3.90971 newtons. And then our right-hand side is F minus FB, so it's 7.5 newtons minus the 3.59 newtons, which is 3.91 newtons. And we can see that to within sig figs, these agree, as we would expect them to. So you can do that as sort of a third check. And to be brutally honest about myself, I actually made the an error in the problem the first time I did it, and I caught it by checking that third equation and finding they differed by too much, so I could go back. My error was at one point I decided that mass 1 was 1.2 kilograms for no good reason, and that threw everything off. It sort of snowballs after that. But anyway, the two things they were looking for are 1.04 newtons and 3.59 newtons.